Hello and welcome to the TelecomTV Summit on 6G Research and Innovation. I'm Guy Daniels, Director of Content, and coming up now is our discussion on the Terahertz Generation. Now, terahertz spectrum promises to offer a whole new level of applications for cellular-based use cases. One innovative application that's showing promise is to use frequencies in the terahertz range to convey sensory signals, to augment the usual audio and video, creating deeper virtual reality environments. And there are many more. But whilst the high frequencies permits vast data transfer, the downside is that attenuation and practical distances can be very short. So, to find out more about terahertz, I'm joined by two leading experts in the field of advanced communications. Professor Aarno Pärssinen of the 6G Flagship project in Finland, and Professor Mischa Dohler of King's College in London. Hello, welcome both of you. Mischa, good to see you again, and Aarno, thanks for joining us on TelecomTV. Now, we're selecting just two technologies for our 6G coverage this year, both of them focused on the radio side. We know there's many more technologies that will be channeled into future wireless standards. But the use of terahertz spectrum is already generating a lot of excitement. Can we establish some basics first? Aarno, what exactly do we mean by terahertz? Because I'm seeing a lot of announcements of work being done in gigahertz bands, really, below 1 terahertz.
Yeah, that's a very good question, because terahertz is lately being used quite a lot in terms of marketing. In frequency domain, we have quite many definitions actually for different frequencies. And now we more speak about, to be honest, upper millimeter waves, which is ranging from somewhere from 100 gigahertz up to roughly 300 gigahertz. So we are really not in terahertz exactly yet, but that starting from 0.1 terahertz is kind of the definition many people are using nowadays, and we are kind of adopting it. Although, yes, to be honest, it's upper millimeter wave where there is a new spectrum available beyond what has been used already, or which is starting to be used in 5G applications even before that.
Okay, Anna, thank you very much. That's good to know. Now, we've seen with each generation of cellular, as we open up new bands, that the higher the frequency, the more data can be transmitted, but it does come at a penalty. Mischa, can you explain to us why we actually even need higher throughputs in cellular, given that there's going to be likely restrictions in what we can use these new bands for?
Yeah, do we need higher throughput? It's a good question, guys, really good question. And it turns out we're always looking for the killer apps when we design new generations, and often in vain. But I'd like to quote a very smart man, the current chief executive of Verizon and the former chief executive of Ericsson, who said, look, guys, we started designing 3G when the internet wasn't around, and we started designing 4G when the iPhone wasn't around. So therefore, we as engineers, we know what the trend really requires. It requires, order of magnitude, increase of data rate and improvement in terms of latency. So all these KPIs are either multiplied by 10 or 100 or divided by 10 or 100. So we do know that. We're starting to get an idea how to do it. And the gigahertz band is probably one of these opportunities. We just don't know really why. So therefore, to answer your question, I don't really know. We need to be patient here. We do have inklings in terms of a holographic society. But if you do the maths, you figure out that probably you can do with much less data rate over the interface. I'm personally excited about another property of these type of bands, the terahertz band, and that is the joint sensing and communication, which opens up so much for the volumetric capturing, holographic projections, etc. But maybe that's a different question to tackle.
Well, there's an exciting range of use cases already sort of coming to light that we're already talking about, and I guess that does encourage a lot of the early research work, knowing that there could be really useful applications at the end of this. Aarno, on this subject of why we need terahertz, we assume that it's going to be really short distances. The higher the frequency, the shorter the distance. But can you get terahertz? I mean, could these frequencies work longer than we originally thought? Because I'm starting to see applications and people are talking about backhaul as well. And I always assume backhaul is going to require quite some distance. It's more than just a few centimeters.
Yeah, this is right, because we need to actually continue the same trend that we started actually with the 5G. So we need to go to directive antennas, and with properly designed directive antennas, we can go longer distances as well. So it's really finding a balance between data rate, longer distances, and technologies what we are using. I see also applications in data centers and in distributing that large amount of data to locally in a, let's say, average distance. So it's kind of a system where you can have radio links with very high data rates for longer distance, and then you design a bit different radios for local and really short range communications. And it will be challenging, but there are examples and there are thoughts and considerations on all of these categories. But definitely it's not going to be the same as the cellular in 4G, for example. So we need to design the system differently overall.
Now, in researching this, I came across a press release from 2015, and this one was from Fujitsu, and it claimed to be the world's first compact transceiver for terahertz, although it was using 300 gigahertz. And it was claiming like 40 gigabits per second over a meter. And that was 2015. So Aarno, I take it we've been investigating this science for quite some time now.
Yeah, this frequency range is not completely new. There are applications and there are radio astronomy and so forth that has been utilized this frequency range already earlier. But of course, this beyond 5G discussion that started a few years ago brought this range now to the cellular communication, which is more like a mainstream thing. And that's why we are kind of need to have different kind of trade-offs to be done to get this frequency band adopted. So it's not totally new, but we don't have yet the equipment that is cost efficient and can be in a way spread for a bigger audience in the level that we see the smartphones being used today and earlier. So it's a technology revolution, definitely, but not totally a new territory for the science.
Well, we'll come on to what equipment and technology is going to be necessary in a moment, but I just want to pick up on how long we've been working on this, Mischa. There was another release, this one's more recent release, I think it was from Samsung, and they were talking about a trial of 140 gigahertz wireless link, 16 channel phased array. Anyway, it was achieving a lot, and they were quoting something like 6 gigabits per second over 15 meters. So we start to see this. We've seen this before in 4G and 5G. These world firsts, and everyone's sort of pushing the envelope a bit. But what would you say is the current state of the art when it comes to research into terahertz for wireless communications?
Well, as Aarno said, the big challenge is really on the device side, and if you look at the data rate achieved, the 6 gigabits per second, this isn't really impressive, right? We have done better in 5G at lower frequencies. In fact, orders of magnitude more than this specific trial. However, the trial is very exciting because it was able to do that at frequencies which normally were reserved for medical devices or for satellite passive sensing, applications. So therefore being able to actually transmit something which isn't just bouncing off some radio frequencies, but actually transmitting information, modulating this, demodulating, decoding that is hugely impressive. And now the next step is really to commoditize all the devices we need to make this happen. And with that, hopefully, we will open up, a new horizon of wireless comms.
Yeah, let's hope so. And that brings us on to what is required to do this. Aarno, you spoke briefly before about this, but what equipment and technology is necessary to support terahertz? What new processes and scientific advancements are we going to need?
Yes, we need quite a lot. But I think the main thing here is to understand that as we go as high frequency as this, the speed of let's say the current state of the art technologies start to be on the limit. And this is of course something that has been discussed for a long time in cellular domain and in electronics. And now we start to be in the range that we might need something new. It's not necessarily fundamentally new, because if we target for 10 years to come, we need to have some sort of a first things happened already. And there are transistor technologies that can make amplifiers up to 1 terahertz range already. But now combining that and packaging that together with the mainstream CMOS, for example, for digital signal processing, requires many steps that are advances both in terms of technology and science. And as we are in the demanding field, there is of course opportunities for new openings. How timely and when they are going to come is hard to predict as well.
Great, thanks, Aarno. And Mischa, I've been reading about the requirement perhaps for new signal processing theories to support this work. Are we at the cusp of moving away from evolution to revolution in how we have to approach the next generation of cellular?
I think from a physics point of view, it is evolution. All of that obeys Maxwell's equations. And from an engineering point of view, Aarno said it rightly, we really need new devices in terms of power amplification, because we're moving into carrier frequencies, which we have never seen before, really, to transmit information. And from a bandwidth point of view, we need totally new electronics, because we just don't have anything quick enough to sample that. So currently we're doing this at 1 bit or 2 bit, which clearly is not enough to get this, at scale, processing the information. But you're rightly asking, is there more to this? And I maintain that, as radio engineers, we often forget that the radio on its own is pretty useless. And I maintain we need an architecture behind this, which is able to absorb these data rates. And I call this an impedance matching between the air interface and the radio access network, and even the transport and core network. There's no use to have an air interface which pumps through, terabits per second of data if you can't really deal with this, neither in the edge cloud, nor from a transport networking, nor from a control plane point of view. So therefore, we need to work together as a community, really, to make sure we build an end-to-end system, which in 2030 or whenever it comes out, is really viable, economically viable. So I think this is something we need to pay attention to.
Yeah, good point, because 6G will be a system. It's an end-to-end system that we will look to specify and standardize as we go forward. Aarno, I read a quote recently that described terahertz as the Wild West of physics and electronics, little understood, even less demonstrated. It sounds a bit harsh, but is it harsh, or is that probably a fair assessment of where we are at?
Yeah, I think that this is kind of everything related to the radio engineering and RF is considered kind of a black magic for the people who are not knowing it. And it requires a long and extensive education to get into the details. After that, it becomes a deterministic science. And that has happened at lower frequencies. There are many people already who start to master terahertz in many of the aspects, and there are more to come once cellular is approaching. So it's not fair to say it's Wild West, because it's really limited by the physics and the laws of nature. But get into it. It's really challenging, and it's very understandable that there are people who might think that this is something that is a black magic. And we need to make sure that this radio engineering stays kind of in a picture, and it's not just a software. We need to get the physical world and the virtual world meeting each other if we want to materialize 6G systems or anything which really utilizes a very broad bandwidth, as Mischa very appropriately pointed out in his previous comment.
Well, it's always very exciting when we push the limits, continue to push these limits. Mischa, the other area we are focusing on in this summit is RIS, Reconfigurable Intelligent Services. Do you think Terahertz is an essential partner to reconfigurable intelligent surfaces? Are these two technologies likely to rely on each other?
Now, I'm not an expert at this specific technology, but I'm a physicist by education, and I know that both obey Maxwell's equations. And by the way, Maxwell worked for a while at King's College in London. So, these are very fundamental laws. And as Aarno said, the equipment doesn't get around that. So therefore, in theory, any frequency could probably work with the intelligent surfaces as long as there's a proper matching between both. But of course, Terahertz is a great opportunity to make this happen because the physical footprint can be much smaller. So therefore, I think there's a great opportunity to explore that. And I'm sure Aarno knows more about this area than I do. But from a physics point of view, I think it's a very general and versatile technology.
Well, thanks, Mischa. Well, let's ask Aarno then. So do you think these two areas could well be complementary, and we'll see the development going sort of hand in hand?
I think they are not exactly complementary. In principle, from physics point of view, you can do these reflective intelligent surfaces at any frequency. And the first prototypes are being done at much lower frequencies. But they might be more attractive to solve some of the problems in propagation and penetration to the materials at higher frequencies. And that's why they are so attractive. So they might be a solution for the let's say systems that can go around the corners and behave nicely. They are a bit like repeaters that were studied extensively in 5G and 4G, and they try to, in a way, improve the range. There are technical components in this technology that definitely should be improved quite a lot. So we will see then that how far the improvements in this area are developing and what is really the final applicability for 6G communications. But definitely an interesting area for research at the moment.
Well, we'll talk more tomorrow about RIS. Mischa, there's broad agreement that terahertz is going to be a major area of interest as we work towards 6G. But as you push forward with research, do you envisage likely use cases? You spoke already about this potentially new area of sensing as applications. There's others that are associated with terahertz. There's backhaul, there's AR. Do you work towards those use cases, or is the work more generic at this stage, with the use cases following as and when?
Yeah, so the co-design, I think, really plays an important role in 6G as it was in 5G. So really going out to society, to industry, to consumers, and ask them the very simple question, if a technology comes out in 2030, which is called 6G, and it is able to transmit, at gigabits, maybe terabits per second of data rate, what would you do with that? Okay, so we're getting first answers. And interestingly, a lot is coming back on this fully immersive holographic type of society. Let's call that generally the metaverse. So where really you can't differentiate anymore between what's real, what's digital, what's being projected, what's being created, what is actually there given by nature versus what maybe your friends are projecting on there, etc. So, and to enable a society like this, clearly a very futuristic society, we need to ship forth and back a lot of data. And if we look at just the simple problem of transmitting a holographic image like my face, we would need in raw format about 4.3 terabits per second as a data pipe. Now, this is, a lot of data, and I cannot see anybody really doing this because we'll be using smart algorithms to compress it, maybe use AI to predict the way how I move my lips and my face. But we are seeing really a requirement for more immersion, lower latency, I'm not speaking about the 5G notion of lower latency at low distances, but really globally low latency. So that I think will be one of the huge challenges really of 6G. And on the back end, you're absolutely right. So we're looking at joint access and joint backhaul. In fact, we had explored that interesting in 2012 as part of the European project, where we looked millimeter wave to be used as joint access and backhaul. Why is that possible? Because at these high frequencies, you can have pencil beams. So you can fire a very dedicated beam with high power into very specific areas, distances, and points. So you can literally direct it between two backhaul links, but you can also point it at the same time, same frequency, using the same power down to a specific pocket or mobile phone. So therefore, this joint access and backhaul, I think, is a really interesting area to be explored as well.
Thanks, Mischa. And Aarno, do you pay a lot of attention to potential use cases at an early stage, or is work still more focused at a basic, more fundamental level?
I'm personally, of course, very much interested really on the fundamentals, because they should be scalable over the different applications, over different domains, different kind of radios. But of course, for that, we are having background some of these use cases that Mischa already mentioned. And for that reason, it's kind of a balance between these two. I think that one of the main challenges is here really to find the right technologies, and that we can do in many ways in quite generic platforms. And that is needed first, that then we can start to really develop these applications. It's the same as with 5G and in earlier generations, that we need to have first the technology. And then there are a lot of users. We didn't anticipate what was the real killer application for the 4G when we started to design it. And definitely we don't know yet it for the 6G as well. So it's good to have some interesting applications in mind and then see what is really happening. So I vote at the moment much on the fundamentals with some application scenarios in mind.
Thanks, Aarno. And finally, let's look at where the main challenges are. Mischa, what is needed between now and, say, 2028, 2030, when 6G technologies might just start to appear?
So in my opinion, it's probably three major steps. One is fundamental research, as Aarno just said, really find out the fundamental enablers which can be scaled. Then translate that into innovation, and there we need capital, we need skills. And then we need to get it into standards and really then start the deployment. So for me, these are the major steps to get this very exciting technology to market.
And you're right, terahertz is very exciting technology. Aarno, from your perspective, what's needed? What are the challenges between now and actually commercializing so we can all start using this in 6G systems?
I'm very much second Mischa in his comments, and maybe it's good to understand that these technologies that we will need in 10 years of time, the basics are there already. So there is not enough time to develop anything just from scratch. And that's why we need to apply them wisely, find new ways to apply them, and then see how far we are when kind of 6G standardization will be starting. And we know that some of the items we have been discussing will get in, some of them may be a bit later in the time scale. We shouldn't forget those, because it's part of the technology evolution that needs to go on without any major disruptions, to be sure that we can actually do future generation wireless communication. And it seems to be continuously a demand to do that. And then the generations will follow when there is a good time and need in the market to adopt the new technologies.
Yeah, a good point. And it's also good to remember that although we say 6G may start to appear sort of 8 years or at the end of the decade, you've got a whole decade of so-called 6G work going on in the standards process, and new features and new technologies will always be required and always be pushed through the standards process. I think that's a good point for us to stop our discussion on terahertz. Thank you both very much indeed for participating and sharing your views with us. Now, if you're watching this on day one of our TelecomTV Summit on 6G Research and Innovation, then don't forget to send us any questions you have and we'll try and answer them in our live after show programme. And that's tomorrow at 4 p.m. UK time, right at the end of day 2. And please take part in our online poll. You can find it below this video next to the Q&A app. We'll be back tomorrow with more discussions for you and of course the live after show. Until then, thanks for watching and goodbye.